Alright everybody, today we're going to do net ionic reactions. What in the world is a net ionic reaction? Well, here's our problem. Remember our friends who are going to prom? Well, for them to be able to reorganize so that the two gentlemen switch which lady they're with, what has to happen is these guys have to break up, right? And these two, my lines are really horrible. These two have to break up. So in reality, what has to happen is all four of them need to be walking around the dance alone. So to break these two, where am I? These two can't get together unless they aren't currently with someone. So they have to break apart. So that's what we're going to talk about chemically, right? And we're going to focus on what aqueous is. Because if we take salt, which is a crystal, it's an ionic compound, and we combine it with water, which is a covalent compound, happens to be polar, which is very important, we end up creating over here salt water. Water with salt dissolved in it. But what really is going on down at the molecular level? Well, when we think of these crystals over here on the left, what are they? Well, they're really a bunch of sodium and sodium ions, which are Na+, together with some chlorine minus ions. And they're right here, and they're in this crystal lattice work that we see over here. But the problem is they get attacked by water. Once you go and you put those crystals in water, water attacks them, and it strips off some of the sodiums and some of the chlorines, eventually doing all of them. But what it does is it completely surrounds the sodium ion with oxygen atoms, which are negatively charged. Similarly, the chlorine is attracted to the positive hydrogens, and so the chlorine is surrounded by a bunch of hydrogens over here. Okay? So that attacking is going on, and as the water sits there with the salt in it, the water molecules are constantly moving, and they're ripping apart the sodium from the chlorine. So all the sodium and chlorine ions are coming into solution. Okay? And that's what's actually going on. So in reality, by the time these are all separated, the sodiums have nothing to do with the chlorines, because the sodiums are completely surrounded by water. And the chlorines are completely surrounded by water molecules. And the water molecules are spending all their time focusing on the sodium or the chlorine. So that's what's going on. So we view these as aqueous, meaning they are completely separate. They've completely separated into positive and negative ions, and the sodium and the chlorine are no longer together in that crystal lattice work that we think of as salt. So those are ions. So what really is going on when we say NaCl and we call it aqueous, that's really a misnomer. That's not really right, because what we really have is we really have sodium ions and chlorine ions running around in solution. And really what we should do is say they're Na aqueous and Cl minus aqueous. Right? So we probably should write it that way, because that really is more what's going on. So let's think of it that way. And then we're going to have some rules for net ionic equations. So please pause the video, write these down. And it's going to be a lot easier to understand when I actually do one, but go ahead and write these down anyway. You're going to, the first thing you do is you write the full balanced molecular equation like you're used to. And then you write a complete ionic equation. Well, what that means is that solids don't ionize, but aqueous items do. They completely dissociate. And subscripts become coefficients, so we'll talk about that too. And then to write the net ionic equation, you have to cancel out all the spectator ions. Think of it if you're going at a dance and you're watching, and you're not actually dancing, not actually participating. So if you have something in the reaction that does not participate, it just watches, then we call that a spectator ion. So the only ones we want to leave are the items that actually reacted. Okay? In other words, changed. In other words, became solids. So let's go and give an example. Solids, liquids, gases. They just changed. Okay, so let's go ahead and try one. Right? So the first thing we have to do is say, Well, barium nitrate, what is going to result from this? Well, it's going to be nickel 3 nitrate and barium sulfate. This is a double replacement reaction. And the question is, does it happen? I happen to know it does. So to avoid a lot of wasted time here, if you want to do it on your own, go ahead. It'll probably be a good exercise. In the meantime, I'll write it here. Barium nitrate plus nickel 2 sulfate will give me barium sulfate plus nickel 2 nitrate. Right, so since it's nickel 2, that's going to have to be a 2. Let's see, barium nitrate. Barium has a +2. Nitrate has a -1, so I have to have 2 of those. And as I look across this, I am balanced. Okay, so that is my equation. I happen to know that barium nitrate is aqueous. Anything with nitrate is aqueous. And nickel sulfate is aqueous. And barium sulfate is the thing that's going to end up being positive. And nickel nitrate is going to end up being aqueous. So what actually happens? So we're going to go and we're going to take this and we're going to write our full ionic equation. So if I look at barium, barium is Ba, and it has a 2+ charge. So that's the way I'm going to write barium. Nitrate is NO3 and has a 1- charge. But you'll notice here I have a subscript of 2 after nitrate. That means I've got 2 of them. So I have to have 2 nitrates. Remember, these things are completely dissociating in water. So I've got barium floating around, and I've got nitrate. Remember, nitrate's a thing. You can't break it up, but nitrate's there floating around, and I've got 2 of them. Right? Now, both of these, of course, are aqueous, because they're both ions. And then I get nickel, which is going to have a 2+ charge, and it's also floating around there in water, so it's aqueous. And I have to add to that sulfate. I only have 1 of those. Sulfate is aqueous, and that's the left-hand side of my equation. Now let me do the right-hand side of my equation. The right-hand side of my equation is barium sulfate. Well, notice barium sulfate's a solid, so we just write that as barium sulfate. And we do not break it apart because it's a solid. Well, we do break apart the nickel from the nitrate. Right? And there are 2 nitrates, and each one has a 1- charge, and nickel has a 2+ charge. All right, so that is our full ionic equation. So now what do? Well, we look for things that don't change. So for example, over here on the left, oops, I'm sorry, I forgot something. Those are both aqueous. I have to write aqueous. Right. This nitrate that's over here, in fact, there are 2 nitrates on the left, both having a -1 charge, both aqueous. And over here on the right, we also have 2 nitrates, both aqueous, and both with a 1- charge. So we essentially can ignore them. So what we're going to do with these guys is we are essentially going to just throw them away, because we say they cancel each other out. They're on both sides. They are, in fact, a spectator. We'll also look at nickel with a 2+ charge, which is aqueous. The same thing on the left-hand side. So again, it is the same on both sides. So we're essentially going to get rid of it because they're spectator ions. So what's left? Well, what's left are the things that changed, the things that are not spectator ions. And that's barium, which has a 2+ charge, which started out as being aqueous, and sulfate, which had a 2- charge. It's also aqueous. And what we're producing is barium sulfate, and barium sulfate is in fact a solid. All right, so that's a full example. Here's another one. Let's see if you can do this one. So go ahead and pause the video. Go ahead and work through it as far as you can, and then come on back and we'll work through it together. All right, strontium hydroxide. Strontium hydroxide and chloric acid. How do we do that? Well, chloric acid, let's see. Let me just go and start writing it. Strontium hydroxide is Sr hydroxide is OH plus chloric acid, that's HClO3, should give me, well, if the H and the SR replace each other, I've got an HOH, what a strange chemical, HOH plus SrClO3. Well, let's see. SR has a 2 plus charge, so OH has a 2 minus charge, has a 1 minus charge, there are two of them. And HClO3 balances, because that's plus 1 minus 1, and HOH is actually water, so we know that. And strontium, again, has a 2 plus charge, so I have to have 2 ClO3s over on the right. If I have 2 ClO3s, I have to have 2 of these, and that will give me 2 H's to go with my 2 OH's, so I've got 2 waters, and I am done. Right? So now, what are they? Solids, liquids, gases, aqueous? What is it? Well, I looked these up on my little chart, and strontium hydroxide is aqueous, and chloric acid is aqueous, and water is a liquid, and strontium chlorate is an aqueous. All right, so what do? Well, we notice that we have, we can write our full ionic equation, which is Sr, 2 plus 2 OHs, and they are 1 minus, and plus 2 hydrogens, plus 2 ClO3s. Now, the 2 hydrogens are positive, the chlorates are negative, and they're all aqueous. Okay. So, now what? The question is, what do we produce? Well, you should be able to look at this and tell what you produce. You produce water. Thank you. Water, which is H2O, and that's a liquid, so that actually changed. So we're not going to break that up. And we still have some other stuff that's aqueous over here, which is strontium, which is a 2 plus. And chlorate, notice we're not breaking up the chlorate because it's a thing. Chlorate is a thing. There are 2 of them, and each one has a -1 charge. Okay, and let's see, strontium is still aqueous on this side, and chlorate is still aqueous. All right, so if I start with my chlorate is aqueous, my strontium is aqueous, so those guys haven't changed. So we're essentially going to cross them out, and we're going to be left with 2OH plus 2H plus. What do you think is going on there? And it's making water. And let's see, that's 2 waters. And that's a liquid. And that is an aqueous. And that is an aqueous. So, that should do for strontium hydroxide and chloric acid. This is my net ionic down here. Okay, last one. Again, see if you can do this on your own, and then come back, we'll do it together. All right, I'm going to do this part quickly. K3PO3 plus MnBr2 gives me MnPO3, and that's 3, and that's 2, plus KBr. It looks like I need 2 of those, 3 of those, for a total of 6 of those. And I need 3 of those and 2 of those, so I'm good. Okay. This thing is aqueous, this thing is aqueous, and I happen to know, I had to look up manganese phosphate. And manganese phosphate is in fact a solid, and potassium bromide is in fact aqueous. So I know what's changing. I know it has to be broken down. So let's try this. How many potassiums do we have? Be very careful there. How many potassiums? We have 6 potassiums. Each one has a +1 charge. And we have 2 phosphates. Sorry. These are wrong up here. Those should be PO4s. Sorry, my bad. 2 PO4s with a 3 minus charge. And we have 3 manganeses, however you pronounce that. And we have 6 thank you, bromines. Now, all of these are aqueous because they're on the left-hand side. And now over on the right-hand side, you'll notice I have a solid. So I keep writing that as a solid. I don't change that at all. And I have 6K and 6Br. All right, and the Ks and the Brs are both aqueous. All right, well, I know you're chomping at the bit to go and get rid of stuff, so I find my 6 potassiums, and I have 6 potassiums on the left, so they go away. And I've got 6 bromines on the right that are all aqueous. I have 6 bromines kind of in the middle that are all aqueous, which leaves me the manganese and the phosphate. So I can write that as 2 PO4, 3 minus, aqueous, plus 3 Mn, aqueous. Mn has a 2 plus charge. Become Mn3, PO4, 2. What's important here, folks, is that is a solid. So what happens is the 2 aqueous have now combined
to make a solid. I say I'm trying to put parentheses around that. It is not working.
All right, so that is it. So it's your turn to do some on your own worksheet. Go ahead and see if you can do that. Take your time. I know these take a while. If you have to be patient and just work through them, take all the steps. Okay? Have a great day. Ask me in class or ask Ms. Sherman in class if you've got questions. We'll be happy to help you. Okay? See you then.